So let's look at the product for logs, which is an identity. So what we have is log base B, and we have a product inside, I call it M times N. This, and again, notice this is function notation, what I'm writing here. It turns out that this is equal to log of M plus log of B of N. Now, that does not appear at all to be intuitive, but it turns out that whenever I see this, I can replace it with this. Okay. Now, where does this come from? So this is not obvious at all. And that's where we need identity. So identities are going to make statements that, hey, by the way, these two are the same, but it's not obvious like the previous example. But where does this come from? It comes from this exponents. Again, logs are just the inverse of exponents. So it comes from this fact. So when I take the product of same bases, notice the bases have to be the same for all this to work. But if I take B of M times B to the raised to the nth power, that's the same thing as writing B M plus N. So again, this is an identity. And we know it's exponential rules. So notice the product rule, exponential rule. But it still doesn't explain the one that I'm seeing here above. How does that work? Matter of fact, I'm going to there. So here's a proof. So we don't do proofs that much anymore, actually at all, but I think it's really important to understand that this is not just a rule. It has to be proven to be correct. So I'm going to do the following. I'm going to let x equal log, not y, no way I wrote y, I'm going to write b. So I want to match what I wrote here. And I'm also going to let y equal to log b of n, just like that, okay? Now, if I change both of these expressions to their exponent equivalent, again, this is what I know to be true. I know to be true. So I have to use this that I know is absolutely true to prove the one above, which I'm telling you is true, but I haven't proved that it's true. So I'm going to change this to exponent form by changing, again, the base, output. Now it becomes the input, input becomes the output. Same thing with the other one. Okay, great. So what do I do now? So again, notice that this involves a product. So I'm going to take the product of these two. So when I do that, on the other side, I'm going to take the product of their equivalents. Again, because these are identities, and that's what it means. Whenever I see this, I can replace it with that. Whenever I see this, I can replace it with that. They're equivalent. So when you're doing equations, you're writing typically identities, sometimes not. But in the case, I'm trying to say they are, okay? Because this is going to be true for everything. So great. How does that help us? Well, again, I know that m times n is going to be the x time plus y, again, using the rule that I know. So now I'm actually using the rule that I said that this comes from. Okay, great. Now we're going to go over here and continue. So what I'm going to do now is write this down here to emphasize this. I have m times n is equal to b x plus y. And now I'm going to take log of both sides. So this will be like taking the square root of both sides, squaring both sides. So both these expressions are going to go inside the log function. Took a little wedge here and it's pushing my pen down. So I can't write normally. It's a bad design. So I took log of b of both sides. How does that help me? Well, notice immediately when I did that, I created this. So I have one part. The question is, can I get this part here to equal the one above? So I'm gonna emphasize this one more time, and I'm gonna write it again, this side, to emphasize the equality. But I'd really notice that log base b, b raised to the x plus y, these are inverse functions of each other. So immediately all I get was, when I have inverse functions, I get the input x plus y. Okay, I can only do that because these are inverses to each other. Now I can come over here and say, well, what's actually x? Well, it turns out I will come back to my original statement, and x is equal to log base b. So I'm going to replace now, substitute x with what it really is, which is log base b of m, and y with log base b of n. And there you have it. There's a product rule. So, and like I said, we're going to use this to prove or do certain manipulations. Let's just do one simple one. Suppose I want to evaluate log base 4 of 8, log plus log base 4 of 2. And again, I don't want to use a calculator. So I'm going to write this down. And what is it that I recognize? Well, according to that rule, I can write this as a product. So I recognize I have the same basis, so, and I'm adding. So immediately I have go backwards, and I could take the product of the inputs, because these are equivalent statements. So now what I have is log base 4 of 16. And what is log base 4 of 16? Well, log base 4 of 16 is really 4 squared. And again, now recognize log base 4 raised to the second power. These are inverses of each other, so the output is 2. Okay. So again, we're going to use these product rule to manipulate some expressions.